Welcome everyone, and welcome back to people who have been following the quantum computing class through comics by Hackaday. So this is our 20th session. It's been quite a while. We started in April, and through Hackaday, I've been teaching this throughout the pandemic. This is every Sunday we're meeting all of you. We also invited a lot of other communities to come in. I think for some people who joined after Microsoft Reactor started advertising, this is session 12, but really I probably should stop counting this because we kind of have merged a lot of communities here. Just a reminder to people who haven't been to this class, all the information is on Hackaday's project, Quantum Computing Through Comics. Every Sunday, unless I announce some special arrangement, like last weekend we didn't have a class, we would have a Sunday for 30 minutes to an hour talking about one topic. And it could be theory, it could be programming. Today we're going to talk about hardware. And after the class, we'll have some Q&A session. We have quite a few community members now working on their respective quantum computing projects who would like to share, so feel free to share that during that Q&A session. Our official documentation is from the Microsoft QSharp documentation, and we also have been using the quantum katas for exercises. For people who missed this, please go back to previous classes and also try some of these hands-on exercises that would help you get understanding of the topics that we talk about. So we have spent quite a lot of time talking about the fundamentals for quantum computing, from concepts to using linear algebra and computing language QSharp to build algorithms. And eventually we're going to run our algorithms on hardware. I actually gave a class on hardware some time ago on May 3rd. So that's in the Hackaday list session 6. If you missed that one, please make sure that you go back to that. I won't be repeating some of the content that I already mentioned in that class. So today we're gonna jump ahead a little bit. And hardware, I guess there are two aspects I want to mention here. One is that right now we have quite a lot of companies that are building cloud solutions. So you're not going to have like a pocket-sized quantum computer anytime soon, but you can use your existing PC or any computer to write algorithms that can access our hardware infrastructure through the cloud. So there are already working quantum computing hardware that we are giving to customers to run their projects on. And the other aspect about hardware is the various types of hardware architecture. So I'm going to give a very quick overview, but we're going to talk a bit more about the topological qubits, which is the architecture Microsoft is pursuing. That's probably conceptually the most unfamiliar to most people. So we're going to talk about that one primarily for this class. A quick recap from the last session 6 that you can look at these past topics, including the different architecture of hardware. Recap is that classical computers is built on transistors as the building block, which are just one on and off switches, 1 and 0, using transistors. And we know that quantum computers fundamentally would need systems that behave in a quantum mechanical way, even though you can argue that transistors are also quantum mechanical, but you need to be able to support the quantum computing methods, meaning we need to use superposition of energy levels. And you need to find systems that offers you those energy levels that could be put in superposition. So a natural example would be something like an electron spin up and down energy levels. And how do you trap electrons? You can put them in quantum dots, which are fabricated semiconductor sandwiching a thin layer of electrons, and then you can confine your electron into only one dimension, and you can trap electrons there and manipulate its spin up and down. So you can create your quantum bit 0 and 1s. But you can also trap electrons in crystal lattices. Here is an example using a diamond. You can actually get a vacancy, replace one carbon with a nitrogen atom, and also carve out a carbon that would create a nitrogen vacancy center that can trap some electrons there. You can also use that. But you can also build much more scalable systems like ion traps. You can have ions spin. You can control which spin state your system is at, and then use that as your qubits. Or you can build artificial atoms like superconducting circuits. That's basically LC circuits that gives you a resonance, and then you can use the energy level that's quantized in that resonance as your qubit states. This is blazing very fast, but for the past recording, session 6, you can take it slow a little bit. And then there's the silicon photonics type of quantum bits. You can encode your states into the photons polarization states. But Microsoft is using this topological type that is very special, quite different from the previous few examples where it's relying on individual electrons or artificial atoms or ions, individual spin level. This is using a collective interaction between a lot of electrons. And we can create some special condensed matter states called Majorana zero modes. And they can be formed on semiconductor, insulator, superconductor heterostructure. Like here is showing a nanowire on top of superconductor. So I'm gonna spend a little bit more time on this particular architecture today. The other ones you can, I think conceptually are easier to understand, but this one I would give some basic ideas for you to dig deeper later. Just some research papers that gives you an idea of how these structures look like. You can have stacks of your aluminum nanowire and is covered with insulators and put on superconductor. You can apply metal gates on them to control. So these are already some papers a while back. There are already a lot of new architecture, new structure of these kinds of nanowires you can look up now. But I wanted to show a picture, just like an actual SEM image of that. So the basic idea of creating a nanowire topological heterostructure is started as a theoretical construct. So you can think mathematically when you want to create or annihilate any particle. You can use these ionization and creation operators to just mathematically represent if you have a particle or not. And you can describe your electron using these operators and say, here I want to create an electron and I have this creation operator. You can further even mathematically write that you can actually represent this whole electron with a Majorana pair, which is a pair of quasi-particle or pseudo, not real particle, but you can mathematically represent them as a pair of a symmetric and anti-symmetric part. And in this way, this is kind of a thought experiment. I'm just using a little bit of math to show you that you can mathematically write down all of the following steps. If you can represent your electron with this Majorana pair, then there's no reason you can't put a row of them together. And you can also mathematically write how this row of electrons will look like. So each of them will have a pair, and they're kind of on their own. But then if you put this whole nanowire on a superconductor, then something could change. The field from the superconductor could affect your electron states in the nanowire. And the pairing could even switch. So you still will have a symmetric and anti-symmetric parts paired together, but then it's between adjacent electrons. So if you put this nanowire on a superconductor and pair them in this way, then your end two states could be alone. They don't have a pair. Now you imagine these are the valid states that all these pairs can sit in. And now if you remove all the electrons, these are still gonna be the states that's allowing your electron to occupy. And you start to gradually fill in electrons, you could end up with different situations. So it doesn't matter how many electrons are in between the two ends, as long as you have two situations that have exactly the same number of electrons in between, you could create a configuration where the two end states are empty, or the two end states are occupied. In the middle here, they don't actually have to matter where exactly the electrons are, but you have to make sure that in these two configurations, the middle ones will have the same number of electrons. They only differ by one electron in these two situations. So when you don't have that electron, the two end states are empty. But if you have that one extra electron, these two states will be occupied. And this way, you can effectively create a 0 and 1 state for qubits. And you can even measure which state your system is at using a global parameter like a conductance. So you can just say that if you measure this kind of conductance is in the one state when these two end states, and they're called the 0 modes I mentioned earlier, they're occupied. Or when they're empty, you could be on this state. When you do a measurement, you see in the conductance. So then you can manipulate to have these two in superposition. And here, interestingly, the energy for these two states are actually exactly the same. They're just differing by this configuration. And this way, you can even use the two states as your qubit 0 and 1s. And I like to make this metaphor, like how do you measure a conductance to know what's going on? So it's kind of like a train that is needing a driver. But in this case, you actually need two drivers. You must have two drivers on both ends to have the train conduct. But then another case would be no drivers and the train is sitting still. So that is a different state. And it doesn't matter how many people are inside, but having the drivers on both ends would make it conduct. This is just a metaphor. Turned out that this particular way of creating qubits is the least error prone comparing to all of the other architecture. It is also really, really hard to make. So this type of qubits are called topological qubit. You really have to go into the math and look at their energy band structure to really understand what's going on inside your actual material. But we often also hear and see a lot of analogy like this is if you have these two items, a teacup and a donut, at very local level, you wouldn't be able to tell what topology. They have the same topology, so you wouldn't tell them apart. Only when you zoom out at a global level, you would then know which is which. So in this case, the topological qubits are not so affected by local errors. You still need to isolate them. You need to carefully set up your system not to be contaminated by the environment, but is much less prone to the environmental error. So a few concepts I want to briefly discuss. To build a topological quantum bit is you need to understand this idea about quasi-particles. So you are using actual materials to make your hardware. And that's often like solid states, metals, and semiconductors or superconductors, where you have these atom lattices, and then you will have electrons going through the lattices, and that's what's contributing to conductance when your electrons are moving through the material, how fast and how mobile they are, defining how conducting your material is. And here's the quasi-particle idea. So you can't individually consider each atom or a particle electron anymore, because you have all these obstacles for electrons to avoid, and there are positive charges which would attract electrons, and the electrons themselves will also repel each other. So collectively, they kind of have to correlate each other's movement, and they have to move together in a collective way. And this collective excitation is called the quasi-particle. Is not a very definitive particle, fundamental particle, but is as a whole called a quasi-particle. An analogy I make is, say you have a room of people, and then some VIP enters. Naturally, some people want to be closer to the VIP, and some people maybe are scared of the VIP and move a little bit away from it. So as the VIP moves around in this room, everyone kind of reconfigured themselves to move together with the VIP. So this VIP electron is kind of a overall carrying an effective mass with them as they move along the material. So this is the quasi-particle that has an effective mass. And that's what we're dealing with when we are setting up these architecture, these materials. And another concept to know about is the statistics of these quasi-particles. You may have heard of the fermions and bosons. They have different statistics, namely that fermions can occupy the if they have different spins, you can have two of them occupy the same energy level, but no same spin can occupy the same level. So they would follow this statistics. They will occupy one by one the energy levels separately. But bosons, they can occupy the same energy level. So you may have heard of the term Bose-Einstein condensate, where you can condense all of the bosons into the same lowest ground energy. But when you have a major Roundnet particle, they behave like neither. Is a quasi-particle. So they behave in a statistic called Anions, and it's different from fermions or bosons because major quasi-particles turn out to be their own antiparticle, and they follow a different statistics. Because they follow different statistics, their behavior, their arrangements will be different from the other types. And the dimensionality will also give you different property for your materials, like electrons inside 3D, 2D, 1D, and 0D will behave differently. And when we have a nanowire, we are effectively confining the electrons into 1D. So it will also have a different type of behavior from other dimensions. So just a little bit about how anions work. And in fact, that these quasi-particles used in the topological quantum computing follow something called the non-abelian anions. These terms come from group theory, where you would describe the statistics of different types of anions. So what is abelian is probably familiar to more people. It just means that is order of the terms do not matter. So if you have two elements in this group, if you change their order, is basically the same thing. You could be adding just a global phase to your state. And when you do some measurements, the global phase doesn't really matter. That's abelian statistics. But if it's non-abelian, then the order of which one is in front of the other would matter. If you change their order, then you are effectively using a unitary matrix to change their orders. And we know about unitary matrices. They're what gates are. Gates are unitary matrices. So effectively, if you can braid these Majorana quasi-particles or zero modes, you could effectively add gates to it. So this is how you can make a qubit and then add gates to it by kind of reordering the anions. So braiding is how you can create gates. And I know that there's been a lot of development, and perhaps braiding is not the only way to create gates, but I'm trying to just give you some basic ideas. And if you want to be very up to date, check out some latest publications from the Microsoft quantum computing research teams. So now you know that you can set up zeros and ones, and you can also use braiding statistics to form your gates. But how do you actually do that in actual material? So you can have a lot of control to your setup. Like I showed earlier in the picture, you can have a nanowire and you can apply gates to it. Turns out if you look at the Hamiltonian for your system, you will have a chemical potential term and a kinetic energy term. You can control the chemical potential by applying different gate voltages. So you could apply some voltage to put your nanowire in a trivial state where your chemical potential is dominating over kinetic term. In this case, that would be a pretty uninteresting or maybe normal, like shown earlier, without that superconducting field effect, where your pairing is within the electrons themselves. But you can put them in this topological phase to when your kinetic term is higher than the chemical potential. Then you would then have this topological phase. So you do need at least 3 anions to do the braiding. So you can set up something like a T-junction where you can apply the different voltages to control chemical potentials in different sections in your junction. And then you're effectively allowing these pairs to change locations. So in this case, you can allow the braiding to happen between anion 2 and 3 by just allowing them to move to a different place on the T-junction. This is a really much simplified picture, but I just wanted to briefly explain that how you can achieve this with actual materials. We also need to cool them down to low temperature. So quite a few quantum computing architecture rely on low temperature. There are a couple of reasons. One is that noise can come from temperature, and temperature in the case of quantum mechanical measurements is our enemy. We know that in materials, when you have any temperature is giving energy to your particles, and they can vibrate, they can jitter. And when your electron is trying to move in your material, the more vibration from the lattice, the more difficult it is for the electron to move through the material. So that is creating a lot of resistance. So resistance is basically noise. If this happens, then it can mask out any of the quantum mechanical behaviors that you actually want to observe. So you need to cool your temperature down to a certain level in order to have these bounce around, these scattering much less than your quantum phenomena. The dilution refrigerator is what we use in the labs that could cool things down to really low temperature. It can go down to like tens of millikelvins, maybe even lower. So near zero, absolute zero temperature, and it requires a very dedicated setup. You need to have like a liquid nitrogen to cool things down to 77 K first, and then cool further down with liquid helium to 4.2 K. That's the natural, just the liquid phase of these elements naturally at this temperature. But then you can pump your system and have different phases of your helium and keep your very bottom part of the setup extremely cold. So then you can imagine that this requires a very careful setup, and you don't want anything outside this region to come in and mess up your system. So the electronic control is very important. Our Sydney team recently, it's been a few months, published a control system. They came up with a very, very delicate setup. Is basically a control chip that you can just have 3 wires coming into your qubit setup and then control a huge amount of qubits just using those 3 wires. It's all online. You can read the blogs on Microsoft's website. So it's super cool. And the last thing, the other reason that low temperature is important is also to put your perhaps superconductors into its superconducting state. And you can have a superconductor that, so basically how superconductor it works is like normal conductor, you have resistance that goes up with temperature. Like I mentioned earlier, that's the vibration of the lattice causes the resistance. But in superconductor, you can have a sudden phase transition at a particular temperature. Then you can make your material into a superconductor. So we want that superconducting state below the nanowires. So we need to cool our system down for the superconductor to work. Usual superconductors have these Cooper pairs where electrons would pair up and they would move like a network without ever bouncing into the lattices. That's how superconductors are, is very minimal scattering. They are put into this below the critical temperature Tc, then in the superconducting state, they can form these Cooper pairs and move without much scattering. And this can provide a protection for your system because you need a certain amount of energy in order to break the Cooper pair and put your superconducting material back into a normal conducting material. So there is an energy gap that you can use to shield your system. So if you can cool it down to the superconducting state, then your system is safe from being scattered around. So that's also why we need to cool it down for the topological setup. So that's all the basic concept I wanted to list. All of these ideas come from mathematics. I just turned them into comics. But if you want to look at the maths, the actual review papers, these are 3 very important foundational papers that establish these theoretical instruction for a topological heterostructure, and also is very, very cool that from mathematics we can construct these ideas, and then we try to follow that in the labs, try to recreate the math in actual materials. So definitely go take a look there. So I mentioned we have some special events coming up. In September, I am inviting a few guest lectures, and also through teaching this group, there are some particular topics I know the group is interested to learn about, and I'm no expert in those particular subjects, so I rather invite these experts to talk about them. And Professor Terrell Franz has been coming to our class. Thank you for supporting the quantum computing education. So he is specializing in quantum cryptography. So next weekend, we're gonna have Professor Franz teach us about quantum cryptography. And then the week after, on the 20th, we're lucky to have Professor Chris Ferry. Some of you may have read his book, his series of books. One of the most popular ones is Quantum Computing for Babies. So we are very happy to have Professor Chris Ferry to come talk about quantum tomography. It's a very interesting topic as well. And note the time change for that one. I will repeat this next class as well. Because Chris is in Sydney, we need to accommodate his time. So this normal time will be too early in their morning. We should make sure that we attend his class a few hours later. So I will announce the actual time there. Then just a reminder that all of the Microsoft software development is open source. And these are our official repositories. You can find this all on our documentation. It's a reminder that you can now already participate and contribute to the official Microsoft quantum developments. We have the documentation, libraries, katas, compilers, runtime, QSharp exercises. They're all open source. So you should take advantage of all these great resources out there. And also to remind you that these are the official Microsoft places. And we also have a great QSharp community. Note that this is an established organization and an official site. I will actually show you their website here. It's a very great community of programmers developing using QSharp. Is QSharp.community. I would highly recommend the audience here go to their community page and look at the projects that the community has been working on. They're also open source, they're open for contributions. So we would love any of you to go to participate, and they also have a great list of resources. And please note that QSharp Community is an established organization, and please do not use their taglines and branding loosely. QSharp Community means QSharp Community. So please respect. Okay, let's finish the presentation for now.